and connection with synchronization. The first one, I mean, is about transport properties of active particles that can go from sheep to bacteria, whatever. So it's pretty generic, them all. And yeah, you need some concepts that I don't know if you have in order to do the exercises. So there's some things that I need to know. For example, how many know how to go from a Langevin equation to a Fokker-Planck equation? So you know how to do it. And the rest means that you don't know how to do it. So only 2 know, really. How many know how to go from Langevin to Fokker-Planck? You 2. And okay, yeah, that's a problem. All right. So what you want me to do? I mean, I wanted to do something that is more evolved, but requires knowing that. So I can give you a recipe how you can go from a Langevin equation to a Fokker-Planck equation, or I can try even to demonstrate how you do that. I don't know. This is not what I was planning to do, but perhaps it's more useful. Let's start a bit with that, and then we go. So Langevin equation is going to be something of this form. And let's say that we do something like this. And here we have a noise. And this, I'm writing things as physicists do. I have an identity problem, so I don't know exactly what I am, but I often like to write things not this way. And okay, so the properties of this guy is the following. This delta correlating noise means that this is 0. And if you get this, you get it. You get the delta. Right? So probably this is white noise, delta correlating noise, that kind of names it has. So there are 2 ways that you can play with a Langevin equation. You can use basically everything that is, you have to give an interpretation of this noise. I will always be using Ito in what follows. There's something else that is Stratonovich. So I mean, it's easier and better to handle Ito, but for many applications, Stratonovich is a better option. So anyway, for us, all along, is going to be Ito. So now, if you have something like that, the way that you want to write this, so this is a Langevin equation. And what you want to do is, you may want to express this in differential form. If you express it in differential form, means that you want to do this. And here, this I'm going to write this way. If I write things this way, now this is more or less straightforward, but this guy is a Wiener process. A Wiener process, now that we will tell the properties from, so you can also, going a bit slow, I mean, going to an integration of these, using this definition and arrive to this one. I'm not doing that because otherwise it will take forever. And this guy, the properties, are the following. This one is 0, and if you have 2, and there will delta correlated if you get 2, but this is a property you need to remember. So the square of this guy, average, is delta t. And this is essential for deriving the Fokker-Planck. And the Fokker-Planck is going to be something that looks, I'm going to give the recipe, and if someone is interested in going into why what I'm going to write is the way I'm going to write, we do it later, right? I demonstrate how you go from this to the Fokker Planck, okay? So the demonstration, I'm not writing it. So assuming that you start from something like this, you will write it this way. I'm going to talk about the probability or density, whatever you want, I mean, probability of finding a particle in position x at time t. So, in fact, I should multiply by delta x and so on, right? So this probability density function. And the Fokker Planck associated to this one will be the following. And this 1/2. I'm doing Ito again, no? In the interpretation of that noise. And so for us, anyway, this is going to be constant, so everything that comes in here is irrelevant. So in the problem, I'm going, so this is the recipe, right? I get this. This goes the deterministic part. This goes the thing that goes there. And depending on, I mean, and we are using Ito. So this is what I give you as a background. So now when you write a Fokker Planck, this is often called a linear Fokker Planck. So if I have interactions, there is something that some people call a nonlinear Fokker Planck. I'm going to call it nonlinear Fokker Planck. And this is going to be needed in what I'm going to show next. So for the moment, just take this, that if I have an equation with noise, I can write the properties of the evolution of my particle in terms of a probability, and this I do it this way. Now, the problem I wanted to discuss with you was the problem of, I'm going from oscillators to spins, and this is, I think, is what I mentioned to you during the first class. I don't know if you remember. That was the following. We had, let's say that the evolution of my particles in space is this one. So this is a delta correlated noise. And I'm going to write this way. Identical, oscillators. And then I'm going to couple them with space through a kernel. They will do this design for me. Oh my God, okay. Alpha J, alpha I. And let's call this way. And this is eta. These two are two different delta correlating noises, and they are always 0 if I look at this. So this guy and this is always 0. I mean, they are independent. What else? Okay, so this is my identical oscillators, and then we do the transformation where I'm going to define this variable that is going to be so if I take the derivative of this guy, this is, so now I need to write this equation. This is what I wanted to do. Yeah, okay. Let's see what happens. All right. So this. Yes. This is this part. I mean, this, plus noise. Minus this. This one I can write, of course, I can express it also like theta j minus theta I, since this is, you see that this is so this goes with this, right? So this is, this I can write it like theta j minus theta I. So with this, we end up having a system that I'm going to write here. So this, for the moment, is the same. And this one, we will just use this new one after the transformation. That means if I'm in the co-moving, co-rotating frame, and this is what I wrote. Okay, so then and now we have spins. What was eta? Eta. And there is something else I can do. I can redefine the time in order to get rid of one variable. This is I'm going to do. I could put tilde or whatever, so without loss of generality, right? I can choose this. Same, I can divide everything by units, choose a unit of, I mean, what is going to be my unit of length. And then basically, we can be working with an equation that is this one. So this is, and this is a system of spins. So far, it's okay, right? All right, so now what I want to do is, I'm going to basically write this is our system. So we went from oscillators to spins, and we want to see what happens with these spins. And I want to show you that how you can prove that there is spin waves and how we can go beyond the Mermin-Wagner theorem and shows why if the spins move, you will get spin waves, why if you get the system active, the spin waves are not allowed, and what else can I show you? And why with the system size get big, you cannot have order. So if I take this system, then I'm going to write the focal plank. And here I'm going to do it the following way. So the system is this. I'm going to assume that initially at time equals 0, I have spins in different directions. So the angle is what I'm calling there theta. And these guys are initially separated, equally distributed in space, a distant delta. And I have a system that is periodic with boundary conditions. The size is L. Right? And now the focal plank associated, I have 2 degrees of freedom, x and theta, and that goes this way. This is going to be, I'm going to write it, this is the probability of finding a particle in position x with the orientation theta, I mean, or the spin at time t. And this goes like, I mean, if you follow that recipe for each component, then you will write what I'm writing. And let me write this way. This is going to be interpreted like an average torque felt by a particle in position x with orientation theta. And this, what I'm doing here is going to be a step to go to a nonlinear focal plank. I'm doing a mean field here. Here there will be an approximation. That is going to come later. So now I go into rho, this, and I put the other terms. So this is a constant, what I have. So you see why I put the 2, so when I square and I put that 2, it's gone. And then we have dx this, and we get this other stuff. So this is the average interaction force torque. I'm going to torque felt by a particle at x, or spin at position x. So you realize when I'm talking about spins, it's the same I'm talking about an oscillator. So if I ask when the spins are all the same, it's the same as saying when the oscillators are synchronized. So you got that there is a one-to-one correspondence between these identical oscillators. So whenever I say order here, means synchronization. So I will not be saying all the time that, and I will mainly thinking of spins because at the end of the day, I'm more used to spins. And anyway, so position x with orientation theta. So this guy should be, in principle, I would like to do this. I have my let me write this way, could be, if I put someone in position x, I have to move around this I would have put is of everybody. I have n of these oscillators, so my size is L, and we have n spins or oscillators, and this is going to be this. This is what I want, right? I put like this because this is not what I'm going to write. Now, that means that I need to know where everybody is. And you can see that one way of interpreting this, to write in this quantity, is to say right? So here, and this is what I'm going to put in there. So this, we really are going to insert it in here. So that means that the equation I'm writing is an integral partial differential equation. Has derivative with respect to theta, x, time, and it does contain an integral in the interactions. So now comes the following. So here, so if I plug this back, and I'm going to do it later, so what you are going to see is that we have this term appears, let's write it. Perhaps it's the easiest way. So I'm focusing on this one. So this, what we are writing is the following. Here, I didn't say, but I'm assuming always that K is equal to, and that in fact I can assume that this one is a function of the difference between the two. Right? So this I will use later, but so I never pay attention which one is the prime I'm writing in here. It's irrelevant anyway. So, and here we have rho. And here we have the other one. And then what we have is this. So this is what we have to deal with at the moment. And here, as you see, we have multiplied by these two. This was the mean field assumption. Why? Because in principle, if I have a particle in position x and with the orientation theta, I could have correlations. So I would need to have the joint probability, knowing what is the probability of finding some other. So here, by replacing by this average torque field, whatever, I'm assuming that this one, I can write it without any correlations, right? So what I'm trying to tell you is that we went into this probability of finding an oscillator here and another oscillator there. We said that this can be approximated by this, right? And we are multiplying these two. And this is the probability of finding one particle. You got. So there is a mean field assumption there. So correlation had been neglected in that sense. So now what we want to do with this is I want to show what is the local solution of this. And for the local solution, so what we need to do is we need to, local solution, I'm assuming that I'm not looking in a space, but I'm looking at a given position. Similarly, I could say that I'm expecting that this one can be expressed like this one, rho theta t. So with this one, if I want to normalize as, okay, now, if this is the assumption. If I am assuming this, that means I don't have any dependency on x. So that means this is gone. So the effects of diffusion will not be there. But anyway, the diffusion I want to not to consider initially because I want to think what is going to happen in this system. I mean, about these spin waves and so on. So anyway, so if I come back, that means all derivatives with respect to x are gone. And now we have to rewrite this system. I mean, now if a couple of few things, I'm going to assume that if I integrate this guy with respect to d theta, I get a 1. And then that means that I could provide a renormalization of, if you think, if I do d theta dx, and this is 0L, if this 0L, and with periodic boundary conditions, right? Boundary conditions. And this is rho theta t. This is what we have to decide what it is. Suppose that if we decide that this is 1, that means that after we do, if we have imposed this and I do the integral, we will be doing rho 0 L has to be 1, which means this guy is 1 over L, right? Okay, so this is all things that we are not very concerned, are details, but anyway. So now I replace this in here. And so since we have rho over everywhere, I mean, okay, I write it this. It's going to be rho, and I continue, right? So it's clear what this is of theta t. So since this is going to be present everywhere, I'm not going to write it. I directly assume that I have canceled that. So it's only one rho 0 that is going to come. Here it's a rho 0 square. So this is the only thing I take into account. And okay, so we have rho 0. And then we have here, this term is in there. But I mean, let me see if I can. This was we have this term, and there is the part related to the integral that I'm putting okay? And this one, I'm going to say that this thing is a not. And then what else do we have? And we have this term here. So if I now, in fact, this one I will call it like this, and not tilde, which I'm going to get with this so that we have one variable only. And okay, so our system got simpler. And not is and this is this. Okay, so if you are familiar with the Kuramoto data at this point, I guess you are, you can apply the usual trick. We will do that, but before, since we have used, and this is essentially a nonlinear Fokker-Planck, we have this nonlinearity, and this nonlinearity here is going to allow us to have a bifurcation. A bifurcation in the sense of a bifurcation, and but also in the interpretation of what is happening, this is going to be a phase transition for us, right? I mean, locally, from being, I mean, from a solution that first thing to say, I mean, these observations are the following. If I look at this, and I ask you to guess a solution, do you get the solution easily from here? If rho is a constant, see what happens. This is 0. These are constants, so they go. An integral over v theta prime, which this is going to be 0, and this is going to be 0. So a constant satisfies this. But if there is a constant, I also want to satisfy these conditions. So that means that I have one solution of this system that I can easily guess, that is that rho is 1 over 2 pi, right? 1 over 2 pi is a solution of the system. And now what I'm going to ask is when 1 over 2 pi is stable and 1 is unstable. So I want to do that you were looking with, when was that? Yesterday? No, on Monday afternoon. This linear stability and bifurcations and so on. So here we will do the linear stability of the solution. So we want to know when is the constant solution stable. So you know how to do this? How would you do it? No? So one way, and this is what I plan to do, I plan to add a perturbation to this, insert it into this equation, and evaluate what happened with that perturbation. I want to know whether that perturbation is going to grow or that perturbation is going to decrease, right? So same as you were doing, Ulrike was indicating with a common ODE. But here we have a PDE. And in fact, we have that integral, so that makes things a bit more complicated. But essentially, it's going to be the same, I mean, conceptually. So, so I'm going to do it there. So the idea is I'm going to look at the linear stability of this thing. So, the perturbation, given that we have in a PDE, is slightly different from what you do with an ODE, right? See, because now you have to say my perturbation So we have our solution. This is the one that we have here. And we have to put a perturbation. This perturbation will have a dependency with time, and will have a dependency with theta. And then, let's say that this one, I could write it like this way. An epsilon that is very small, and this. And I want to see whether this is going to grow or not. And this, I will insert one ansatz, one possible perturbation that is the following. And if you have something where the PD depends on x, you will write kx and so on, right? So this is very generic. In fact, it's like doing Fourier. We are doing sort of Fourier by inserting this. So now, that means that if I take this, so the question is the stability, the linear stability of 1 over 2 pi, right? So this is what we are studying. And this is our equation. So when I take this one and take the derivative with respect to time, linear stability means linear in epsilon. I'm going to throw away whatever thing that is non-linear in epsilon, right? So first I take then this guy, rho, is going to be epsilon lambda, and then I'm going to say this is phi, right? And phi. And now I have to do this in this part. So let me start with this one, which is easy. Yes, this, right? So all this, then we will throw away the epsilon, the phi, and we will get an equation for lambda. This is the goal. And now we have this part in here. This part in here is the one that we have to think a bit. And we have d theta, and then the n naught, and then what you have is d theta prime sine theta. And then I'm going to write these things that we have written, which is 1 over 2 pi epsilon, yes, phi t, this, right? So now happens the following. If I do the multiplication of this, you will get one term that is 1 over 2 pi square, right? This times this. But then you have 1 over 2 pi that multiplied by this and this, right? So then you have epsilon, yes, and plus this product, but this is epsilon squared, so this one I can ignore. Now I take this and I take this integral with respect to the sign. So this, when I take the integral, this is gone. When I take the integral with respect to d theta prime, I can ignore what is happening with this, so this is going to be gone. And this we ignore it because epsilon larger, so the only thing that remains is this one, right? So if I do this, you get And there is 2 pi, and there is this epsilon, which I can put in here, and we got lambda t. Right. And this one, so now I'm writing this term is the only thing that survives, and this one you can write this. Now you can try to interpret what is going to happen with this. This is cos. And you start to do the integration. Now, the integration, since we have, you see, if I multiply this with this will be 0 always, right? So the only, I mean, now we have the possibility, this one will get a delta n1 pi from this. You understand what I'm saying? So I'm using the, we are using that. So this is going to be 0 for all, except when this is n equal 1, right? And this kind of stuff. So I'm doing the same with this thing. And then you see that the only terms that survive is when the n is equal to 1. So the entire thing here will look like I think this was I E lambda t and theta and pi delta and 1. I mean, you can verify, I can check if you want, but let's say careful, check. But now what I can do is I can take the derivative, I mean, I have to take the derivative with respect to this guy in here, right? And okay, I forgot all these things over here. So here was the n naught, epsilon, and 2 pi, so which means that this go with this, and that's it. Now, when I take the derivative with respect to this guy, what it's going to bring is we get a I squared from getting, I'm doing this, I mean, I suppose that you are understanding what I'm trying to do. So just carrying out the calculation, and this is going to be minus I squared plus, right? We have minus I squared epsilon 2 e lambda t and an n and then 1 and that's it from this term in here. So now let me summarize the entire thing that we said. We obtain something that is telling us the following. From all this is lambda is equal to something that is, I forgot about, I mean, I'm not getting epsilon, right? So I'm divided by epsilon and so on. So I'm putting the result. And 0, 2, this is a 1, and this is minus d theta n square Yes. And this is a delta, n1. So that means n larger than 1, for all n larger than 1, what you have is that delta, if you want n is equal to minus d theta n squared, meaning all these modes are stable. And you have n1, and this is the only one that is going to make things different, and this is, that comes from here, is the, and this one can get positive, right? So this is the only thing that we are trying to say. And since now, if we have that, so probably we can, if d theta smaller, I mean, that is up, whatever you prefer to write. So when this happens, this is unstable, right? But what is happening is that there is only one mode that can make this unstable, is n equal 1, and it's telling you that there is one peak that is emerging. Of course, you can do it by the trick that we will do in an instance, but basically here is telling you that d theta, when d theta becomes smaller than n naught divided by 2, that we can have, if we define this to be 1, is d theta less than 1/2, this solution that was, when this happened, then 1/2 pi is no longer stable. And that means that your system should go somewhere. And the question is where the system goes. And to see where the system goes, we will take into account the nonlinear part, I mean, this Kuramoto trick. So for that, so what I'm going to do is, where it was this? I'm going to take this. At the moment we are playing, we neglected this. It's a local solution. Here was an n naught, and we have this part in here. So I'm going to go with that part. Yeah. If you rotate what? Yes, d theta is a noise, so you don't rotate here. I'm in the co-moving frame, so it's a noise. If this noise that is kicking the particles, if the noise is too strong, that solution is stable. And so 1/2 pi is the solution of your system. But if the noise is very weak, it's the other way around, it's very weak, it's weaker than this, now the guys will be able to align and point in the same direction. So if this happens, this solution 1/2 pi, I mean, is no longer stable, but we know more. One mode, n1, will increase. And n1 means one peak, right? That means, I mean, this kind of solution. So somewhere, the spins we are a local solution, so they start to point in some direction. Small modulation. So basically, if you think in a circle, and this was the interpretation of, I have spins that are pointing in all possible directions. After this condition, then what happens is that we have something slightly deformed. It's no longer, so there's more probability of finding particles, let's say, in this area, right? I say it's a picture, but it's trying to give an idea of what is happening. So now that means a direction will be favored. So there is a spontaneous symmetry breaking that needs to be happening here. And now what we can do is that trick. Let me apply it. And so so this was the answer when 1/2 pi is stable or unstable. we will look at one becomes unstable because that means that something else has to be there present in the system. Okay, so I put it back. I mean, and now we are back to the nonlinear link problem. That means I want to solve this one. Okay, so there we are. And so now, that is a fantastic trick, is to say, let's introduce a definition. The definition is going to be the following. Let's say, I mean, the problem here is this guy in here. So we will get rid of this guy by doing the following, by introducing, if I say that this is, by definition, I'm defining it as v theta prime then I will be able to handle that. Now I'm going to do a little thing in here, which is the following. I'm going to say, if I do minus a theta, and I multiply both sides by the same, hope you manage to see, that means this part in here, you see what is happening, right? So this guy is R this. And this one, well, I'm writing this thing is this was this. The idea of rewriting the entire part, the integral, this way. So this gets so there is, of course, this is cheating, but we are trained for doing that. I mean, right? So this, why I say it's cheating? Because these does contain information about the raw. So, and now what we can do is quite easy. If suppose that this one, let me write it this way. So this is the same as before, right? So what I'm taking the derivative with respect to all of this. So now, let's look for steady state solutions. So steady state solution means this is 0. And if this is 0, that means that this thing that is in here has to be a constant. And if I'm interpreting this like a continuity equation, which it is in the form that I'm talking about, I mean, I'm expressing it, suppose that I write this like J, and I want absence of probability flux, this constant has to, I mean, this J has to be a constant, and that constant is going to be 0, the one that I'm going to use. So at the end of the day, we are asking that this thing in here has to be a constant. That constant I want is 0. So I write, I suppose this, you have seen it already. Is this. So now I will make use of the blackboard. So this is the same like putting the equal here, right? If I put the equal here, I can divide by this guy as well. And this is what I need to solve. Clear? So this is, if I get this guy to the other side, now the only thing needed to do is to take the integral of that. This is the derivative of the log of rho. So now if I take the integral, that is going to be the log of rho minus rho 0, whatever. So there is a constant. So let me write this way. And this is the integral with respect to theta that is in here, right? And this is going to be the cos of psi. Yes, I got the cos. There is a minus that comes out, but there is another minus that comes. This, though, is this, right? So that means that rho theta t is the n, which is a normalization constant of the exponential of n naught r d theta cos psi theta. And what is this? This is the von Mises distribution. And the von Mises distribution is the Gauss distribution in 1D when you have periodic boundary conditions, right? So this is what you get. Moreover, if you want to see which n is the normalization of this guy equal to 1, we said, right? So this one, n, I can obtain it by in the integral of this guy right? And this is the modified Bessel function of first kind order 0. But doesn't matter, it's this thing in here, right? So this guy is modified Bessel of the first kind. The first kind, order 0. This one. So that thing is, if I remember correctly, is this. You check. This is modified Bessel. Bessel of the first kind and this thing. So, fine. Self-consistency condition. Do you remember how, I mean, how I get this? You get back into, I can use this, right? That we have not been using too much. This one, what we said is mode, a mode. All modes are stable. I mean, if you excite with any other mode, will decay. And there's only one mode that will basically not decay. N1. I mean, yeah, we can do, I mean, what you are going to see in R, you are going to see what is happening. In fact, what is happening in here is that you have a solution that, I mean, there is a vector that can emerge, right? One direction that you like, but they generate the kind of solution that you can have. This psi could be any angle, right? So we have pick up 1. Let me go a bit further, and perhaps that if we can write an equation for R, which is what I'm going to do, and perhaps this clarifies that issue. So this is, we wrote that thing in there, so now I can say, fine. I said at the very beginning that R was this guy. And that is, by definition, we said, that is, you remember that was getting this integral, right? Writing with exponential. So that was, yes, that was the rho theta, and that was our definition. But here I'm going to write explicitly what we said. And no, there is all this stuff in there which I cannot see, and not R d theta. And Bessel. Okay. What? Okay, but the cost I can do is the same, right? Cos of x is the same as cos of minus x. So, but anyway, if I wrote it that way, I put it that way. I wrote it this way? Anyway, so you understood that it's irrelevant, right? So anyway, so since any angle is the same, in principle, we assume that we can break the symmetry in any direction. I'm going to pick up psi without loss of generality. All right, let me write it directly. This R is yes, it's a minus, but cos is what we said, right? So anyway, so this is this way, and we have this guy here, which is a constant, and there is a bit more. This one is cos theta, and well, this is not that obvious, but if you take the integral of the sine prime with respect to this, will be 0. Now, the only one left is this one, and that means that this guy in here is going to look like 1 over this I0 integral of cos oh, yeah, of course. All right, and this one is the Bessel one. Then we have R. So where is one solution in here, which is pretty obvious? If this is 0, this is 0, right? Because I'm integrating from 0 to 2 pi. So R0, then the entire integral is 0, and satisfy the equation. So R0 is a solution. I mean, this is a transcendental equation, and this one is what is called the self-consistency condition, right? Is a self-consistency condition. Self-consistency condition. So where we have R here and R here and there. So we see R equals 0 is a solution. R equals 0, because of the normalization, that has to be the solution is 1 over 2 pi, right? And then there is this other solution for R different from 0, and then we have an R larger from 0. When that happens, I mean, you can try to solve this, but there is another way that you can do this, is that if I go and expand one, I mean, do a Taylor expansion of this, you can see that I cannot stop at order 1, because at order 1, I'm going to get a trivial result, R equals 0. I have to go another order, the second order. If I go to the second order, it's not going to work. I mean, then you have to check it, but I mean, will be vanished, and we will need to go to the third. So we will get, I mean, a cubic term. That cubic term will have one solution that I can take out, that is R equal to 0, and there is another that is the solution of what I mean, you understood what I'm saying. Anyway, you get this polynomial. And so for the R, this look pretty much like one branch, 0, that I have always, another branch that will, I mean, basically take off after the critical thing. The negative part makes no sense because of the definition of R, which I assume that is negative, but that already smells like pitchfork-like, right? Okay. So I have a bit of time still. No, but yeah, okay. I will tell you what I'm going to do. So now what I want to do is I want to plug in basically this equation didn't have this part that was depending on x. So what I want to do is put back the dependency on x and repeat that part of the calculation. After doing that, what I want to do, so I need, let's say, 30 minutes to go till the end. So it's no possible I can do it. So, but then if you put the space there, so where we'll get an assumption and showing, I mean, then we will go to the spin waves. And at the end, the idea was to show you that these spin waves can get unstable by playing with the x, by making it bigger. We were, I mean, able to, this is making unstable spin waves. So the only solution that will remain is the one corresponding for well, that will be coming later clear, the homogeneous order solution. So all spin pointing in the same direction. So dx will promote the existence of order in the system. But if I fix d theta and dx and I increase system size, I will see that all spin wave solution should coexist, I mean, can coexist with the homogeneous solution, implying that order cannot emerge in the system. And then in this way, we will generalize the Mermin-Werner result for 1D for a non-equilibrium, the non-equilibrium situation where the spins move around. And then I wanted to put the coupling back with activity and showing why in active matter, I mean, if particles are self-propelled, spin waves are not possible. And that was a very short argument because that will become very straightforward. And that's it. That was what the plan.
Thank you very much. Any questions? Oh, there, Pablo.
So, what's the difference
Oh, okay, yes. R is defined this way, as I wrote in here, is the polar order parameter. So it's the equivalent to the magnetization, is the magnetization. I mean, if R is 1, means that all spins are pointing in the same direction. If it's 0, means that are all pointing in different direction. And then you have intermediate values between 0 and 1.
And this is already in the definition of the trick step,
yes,
right?
this trick, if you think about what we are doing, is summing in complex space vectors, right? Because you could.
Yeah, it's the magnetization. Yeah.
Yes, I could have done it this way, right? I sum over everybody in here. That is my component in mx, and I can do the same. This is in x, and the other is sum. I mean, divided by 1 over n, right? And you do the same with the other in y. So that would be the magnetization in y. And here what we are doing is basically this one is the imaginary part and the real part.
And psi is the symmetry breaking angle.
Yes, psi is in which direction the spins, yes. Yeah, and yes, then the idea will be saying that this one is a different position in space, might be a different psi. And then we will carry out, continue with the calculation.
Thank you.
All right.
Any other question?
I think no.
No? Well, thanks for today. Just one thing. Do you want to continue this afternoon, or you prefer tomorrow afternoon?
No, I could do it today. I mean, it depends. Perhaps it was too boring for most of them.
No.
I can go into the demonstrating the focal length. If someone is interested, if not, I mean, if I have clients, I will do it. If not, no.
Okay, so, I mean, what do you prefer, the participants? Say it loud. Today. In the afternoon is the colloquium until 3. Usually goes a few minutes longer. And then we have the coffee break. So starting around 3:45 or so. I mean, is that okay?
I mean, perhaps too late and they prefer to, I mean, this is for me the same. I'm going to be around, so.
So, what do you prefer? Well, yes. They prefer tomorrow, because tomorrow afternoon we have some presentation for whoever has been working and has something to tell us about the problems given. So, so I don't know how many we'll have. I doubt that we'll have many. So.
I think there's probably just a couple people here that this was really relevant to, like you guys. Maybe you could just finish it for now, and the other people could go to lunch. And you said it's just like 20 minutes, right?
Yeah, I mean, that is as an option to be afforded, but then it's the other talk, right, by someone.
What? When?
Today.
You mean to finish now?
Here for the ones that are interested.
Well, but I mean, I doubt that you'll have time to eat before 2 o'clock. I mean, that's the problem. That's why we are finishing now instead of at 1, because the colloquium is at 2. And if you continue for another half an hour, the lunch is going to be too tight. That's why. So, okay. So, well, then, let's do this. If at 3:45, this thing has enough people for him to to finish a lecture, so it will be here today. If not, we'll do it tomorrow. We'll see one. Okay. See you too late.